The birth of everything. A journey beyond the Big Bang. Before there was sound, before there was light, before even the whisper of time, there was nothing. Not an empty space, but the absence of space itself. And then, in a moment so brief that even eternity could not measure it, everything began. The Big Bang wasn't an explosion in space, it was the birth of space. The instant when the universe breathed its first, matter and energy, time and gravity, all burst forth from a single, unimaginable point. Yet for all its brilliance, that moment remains one of physics' greatest enigmas. What triggered it? What existed before it? Even the greatest minds, Einstein, Hawking, Feynman, stood before that question in silence. But recently, a new voice has joined the cosmic conversation. Kenji Hamada, a Japanese physicist whose daring theory, renormalized, background-free quantum gravity, proposes something extraordinary. Hamada's work doesn't just patch the rift between quantum mechanics and general relativity, it seeks to rewrite the very language of the universe. The problem that shook physics. Modern physics stands on two pillars. Einstein's general relativity, describing the vast and the massive planets, stars, galaxies, and quantum field theory, ruling over the tiny and the uncertain atoms, quarks, and photons. Each works perfectly in its domain. Yet bring them together, and the mathematics collapses into chaos. The universe, it seems, refuses to be split into large and small. Near a black hole's heart, or at the dawn of time itself, both realms collide and our equations crumble. This is the puzzle that haunts physicists. Why can't the two truths coexist? Hamada's vision, a universe without a stage. Kenji Hamada proposes that perhaps we've been asking the wrong question. In his background-free quantum gravity, space and time are not the stage upon which the cosmic drama unfolds. They are actors, born from the play itself. The universe is not built upon space. Space emerges from the tangled web of quantum interactions. In Hamada's framework, there is no need to quantize gravity like we do with light or matter. Instead, gravity is a reflection of how space-time itself reconfigures as quantum fields evolve. The universe, then, didn't explode into space, it generated it. The Big Bang wasn't the beginning of space, it was the moment space began to exist. A new look at cosmic mysteries. This elegant view sheds new light on old puzzles. Inflation, the mysterious ultra-fast expansion of the early universe, may not require an exotic particle or a cosmic inflaton. Instead, Hamada's equations suggest inflation could arise naturally from quantum fluctuations of space-time itself, a cosmic self-stretching. Dark matter, long hunted but never seen, might be a mirage born of how we interpret gravity's geometry. If space-time itself behaves differently at the quantum level, the unseen mass may not exist at all. It may simply be gravity's hidden dimension at play. And black holes, those terrifying gateways of nothingness, may not destroy information after all. In Hamada's framework, information doesn't vanish. It diffuses into the shifting quantum structure of space-time like ink dissolving into water. Before the beginning, but what came before the Big Bang? In Hamada's model, that question itself dissolves. There was no before because time did not yet exist. The Big Bang was not a moment in time, it was the creation of time. Asking what happened before, it is like asking what lies north of the North Pole. The answer isn't hidden, it's simply undefined. Reflections. Beyond science. Perhaps this is why physicists hesitate to answer the question. Because beyond the equations, it touches something deeper, the mystery of existence itself. The Big Bang is not merely a scientific event. It is a philosophical awakening. It asks, why is there something rather than nothing? And perhaps, as Hamada's theory whispers, the answer lies not in chaos, but in inevitable emergence that from the potential of nothing, reality must arise. The dawn of a new physics. If proven right, Hamada's vision could bridge the impossible gap that has divided physics for a century. It could reshape our understanding of everything from the moment the cosmos was born to the quantum heartbeat of every atom. For now, it remains a frontier, a shimmering horizon, where mathematics meets mystery. But that is the beauty of science, to stare into the infinite and dare to say, let there be understanding. The dance of gravity and the quantum dream. For 3 days, imagine stepping through a doorway into the future, where the pulse of artificial minds beats beside your own. You'll learn how to harness the quiet power of neural networks, not as a distant technology, but as a living tool that bends opportunity toward you. Within hours, you could shape a second stream of income, steady, safe, flowing alongside your main work crafted in just 2 hours a day. No risks, no fear of losing what you already have, only expansion. So go ahead, click the link in the description, join the Universu workshop, and discover the craft that might define the next era of your life. But for now, let us return to the mystery that started it all, the theory of quantum gravity. When two worlds collide, every force in nature has a story. Gravity's story, perhaps, is the oldest, woven into the curve of planets and the pull of oceans. For centuries, we imagined it as an invisible thread binding all things. But Einstein changed everything. His general theory of relativity whispered that gravity is not a force at all, but the very shape of space-time, bent and rippled by energy and mass. In Einstein's grand tapestry, massive stars do not simply pull smaller bodies, they warp the fabric around them, creating valleys in the geometry of the cosmos. Planets fall not because they are tugged, but because they are rolling downhill through space-time itself. It's an idea so elegant, so intoxicating, that it still feels like poetry written in the language of mathematics. Yet, even Einstein's brilliance has its boundaries. His equations rule the vast galaxies, black holes, the expanding universe, but stumble when faced with the infinitesimal. Atoms, quarks, photons, the quantum problem. Enter the quantum realm, a domain of flickering probabilities, where particles dance between existence and oblivion, and certainty itself dissolves. Here, the uncertainty principle reigns supreme. The more precisely we know a particle's position, the less we know its momentum. The closer we look, the blurrier reality becomes. Now, try to place Einstein's gravity into this trembling world of uncertainty, and everything breaks. How can we define the curvature of space-time around a particle whose energy and position refuse to stand still? The gravitational field of a single quantum particle begins to shimmer, twist, and fluctuate. What was once a smooth geometric curve becomes a foaming sea of probabilities. At scales smaller than imagination itself, less than 10 to the power of -35 meters, the universe becomes restless. Quantum fluctuations ripple through space-time, birthing and annihilating virtual particles, ghostly entities that flicker into existence for a heartbeat and then vanish. These ephemeral visitors may be invisible, but they matter. They distort everything: the electromagnetic field, the strong force, and even gravity itself. The closer you approach a particle, the more these phantom particles awaken, humming with higher energy, disturbing the very structure of reality. Soon, the original gravitational pull of the particle, the quiet whisper of its mass, is drowned beneath the thunder of quantum noise. Gravity dissolves into quantum foam, a storm of invisible motion, too wild for Einstein's equations, too vast for classical reason. The quest for harmony, this is the riddle that drives modern physics. Two truths, relativity and quantum mechanics, both perfect, both proven, yet utterly irreconcilable. One describes the grand cosmic dance, the other, the restless heartbeat of the atom. Between them lies a chasm, a place where mathematics falters and imagination trembles. To bridge that gap, we seek quantum gravity, a theory that will unite the infinitely small with the infinitely large, weaving them into one eternal law. It is the philosopher's stone of physics, the unspoken dream of Einstein himself, and perhaps the next revolution waiting in the dark. The music beneath the equations. Think of it this way: Einstein gave us the symphony of the stars, majestic and smooth. Quantum mechanics gave us the rhythm of chaos, sharp and unpredictable. What Hamada and others who chase the dream of quantum gravity seek is the hidden melody that binds them. A melody that might explain not only how the universe moves, but why it exists at all. So as we return to our screens and simulations, teaching machines to think and humans to dream, we are perhaps unknowingly echoing the universe itself. For both neural networks and galaxies are born of one impulse: the drive to organize chaos into meaning. The same impulse that once transformed nothing into everything, the same pulse that began with the Big Bang and still beats, quietly, in you. The ultraviolet catastrophe where infinity dares to speak. In the heart of every equation lies a whisper, a plea for understanding. But sometimes, that whisper turns into a scream. Physicists call it the ultraviolet divergence, a haunting name for a problem that defies logic and mocks our confidence. It is the point where the mathematics of the universe breaks down, where our proudest theories spiral toward the impossible. Infinity. This isn't just a curiosity of gravity, it is the shadow cast by every quantum field, every fundamental interaction that shapes our world. Electromagnetism, the strong force that binds atomic nuclei, the weak force that drives the sun's fusion. Each bears the same curse. When we peer too deeply, when our calculations reach the tiniest scales, the numbers explode. Reality fractures beneath the weight of its own precision, the birth of a trick called renormalization. But human curiosity is stubborn. Faced with infinity, physicists refused to retreat. They invented a mathematical alchemy, a brilliant sleight of hand known as renormalization. The core equations remain the same, elegant and pure, but the constants that define them, the electron's charge, the fine structure constant, were no longer truly constant. They became living quantities, shifting, breathing, evolving as one ventures closer to the heart of matter. At great distances, where quantum fluctuations are silent and space seems smooth, these constants appear fixed, steady as stone. But the closer we move toward a particle, the more reality quivers. Virtual particles blink into existence, ghostly ripples in the quantum sea. They crowd around the electron, warping its electric field. And so, the effective charge, the charge we actually measure, seems to grow stronger the nearer we get. The electron appears to gain power not because it truly changes, but because the quantum vacuum around it conspires to amplify its voice. What we call charge becomes a mirage, a mathematical reflection of the vacuum's restless storm. Renormalization is not just clever, it is survival. It is the act of bending mathematics to save meaning. It's as if the universe were saying, "You may approach, but you will never touch the heart of me." Infinity, the forbidden frontier. In theory, these renormalized quantities grow without bound, as we shrink the distance between objects toward zero. Both in electromagnetism and in gravity, the constants race toward infinity, a place no equation dares to tread. Infinity is not a number. It is a void, a signal flare in the dark that screams, "You've gone too far. Your tools no longer work here." In quantum electrodynamics, this abyss lurks unimaginably deep at distances of 10 to the power of negative 290 meters. That's not just small. It's beyond metaphor, beyond comprehension. The Planck length, the ultimate grain of space-time, the smallest unit modern physics recognizes, is an eternity larger, a modest 10 to the power of negative 35 meters. By the time our equations collapse in QED, we've already passed far beyond the realm where space and time have meaning. Down there, even the idea of an electron becomes nonsense. And yet, within the range of our instruments down to about 10 to the power of negative 10 meters, 1,000 times smaller than a proton, the electron's measured charge increases by a mere 3%. 3. That's it. So small a shift that, for all practical purposes, the theory still sings in perfect tune. That's why quantum electrodynamics is hailed as one of humanity's greatest triumphs, a theory so accurate that it predicts nature's behavior to the 11th decimal place. It dances with infinity, but never falls. The gravity of despair. But gravity is another story. When we try the same renormalization trick on the force that binds planets and stars, the equations refuse to obey. The gravitational constant doesn't just creep upward, it explodes. Even at the Planck length, where space-time itself begins to shimmer into uncertainty, the quantum foam overwhelms the very notion of gravity. At such scales, the gravitational field of a particle is devoured by the chaos of virtual particles. The clean lines of Einstein's space-time dissolve into a storm of creation and annihilation, a maelstrom of possibility where no geometry can survive. Renormalization, that beautiful bridge for electromagnetism, becomes a rope of sand here. The cosmos itself seems to whisper, gravity is not like the others, where mathematics meets mystery, and so we arrive at the edge of knowledge, the place where numbers yield to silence. Infinity isn't just a failure, it's an invitation. A hint that beneath the equations lies a deeper truth we have yet to grasp. Perhaps gravity is not a force at all, but an emergent phenomenon, born from the quantum breath of the universe. Perhaps time, space, and matter themselves are illusions, patterns rising and fading in an eternal field of probability. Every divergence, every impossible infinity is a flare in the night sky of understanding, a marker that says, here ends what you know. Beyond this lies wonder, the fractured crowbar of the cosmos, where gravity refuses to bend. There is a cruel irony in the architecture of the universe. The weakest of all forces, gravity rules them all. It binds galaxies into spirals, sculpts the paths of planets, and bends the light of distant suns. Yet, when we turn our gaze inward, into the trembling realm of the quantum, this mighty force withers to a whisper. At subatomic scales, it all but disappears, so faint, so elusive, that even the smallest particle seems to ignore its call. And this is where the great problem begins. Physicists, bold as ever, have tried to quantize gravity to bring it into the same shimmering framework that governs light and atoms. But every time they reach for it, their equations snap like a crystal crowbar, beautiful, fragile, and utterly useless for the task at hand. The very tool meant to pry open the mysteries of space-time shatters in their hands. What works so elegantly for electromagnetism collapses when turned upon gravity. Why? The answer, as always in quantum physics, lies hidden among the ghosts, the virtual particles that flicker into and out of existence in the vacuum's eternal dance. The whispering sea of virtual particles. In the quantum world, emptiness is never empty. The vacuum seethes with invisible life pairs of particles and antiparticles bursting into being for a heartbeat before vanishing again. Each carries charge, mass, and energy, and though their lifespans are infinitesimal, their presence leaves fingerprints on reality. In electromagnetism, only charged virtual particles matter. But charge is sacred. It cannot be created or destroyed, only balanced. For every electron that appears, a positron is born beside it, opposite in charge, equal in magnitude. Their total charge is zero. The cosmic books remain balanced, but the symmetry is not perfect. The virtual pairs cluster unevenly around a real charged particle. Those of the same sign are repelled, those of opposite sign drawn closer. The result is a subtle distortion of the vacuum, a faint polarization that gives rise to a tiny electric dipole. The effect is delicate, almost imperceptible, and grows only gradually as distance shrinks. Thus, the quantum field hums quietly around an electron, a low murmur of order in the sea of chaos. But gravity plays by different rules. Gravity, however, is the rebel in the orchestra. It does not care about charge. It sees only energy, and in the eyes of gravity, everything, particles and antiparticles alike, shines with the same luminous weight. There is no cancellation here, no balance. The energies of all virtual particles add together, amplifying endlessly. And so, as we peer deeper into space-time, gravity begins to scream. Its quantum fluctuations rise like a storm tide, swelling with every fraction of a meter we descend. What began as a ripple becomes a roar, a chaos so fierce that even the fabric of space-time begins to tear. This is why physicists say general relativity cannot be renormalized. Its infinities are not tameable. The equations blow apart long before they can yield answers. What renormalization gently patches in electromagnetism, it cannot save in gravity. Yet, without a quantum theory of gravity, we are blind to the heart of creation. We cannot peer inside black holes, where space-time folds upon itself like molten glass. We cannot understand the first flickering instant after the Big Bang, when the universe was smaller than a single atom, when gravity and quantum mechanics were one. And without such understanding, we cannot hope to write the final chapter, the theory of everything, a single, elegant equation that binds all four fundamental forces into one symphony. The dream of Weinberg. In 1976, one man dared to chart a path through this chaos. Steven Weinberg, one of the titans of modern physics, co-founder of the unified electroweak theory, looked upon the broken mathematics of gravity and refused to accept defeat. He proposed a radical idea, a gravitational theory that could be asymptotically safe. In everyday language, safe meant this: as we approach the smallest scales, where other theories shatter, gravity would not spiral into madness. Its equations would remain well-behaved, even at the Planck length, the smallest imaginable unit of space. Weinberg's insight was deceptively simple. If quantizing Einstein's equations causes them to fail at the quantum frontier, then perhaps we should not discard them, but evolve them. Let the constants themselves, Newton's gravitational constant, the cosmological constant, flow with scale, changing smoothly as we zoom in or out. These running constants, as he called them, would shift and adapt like living things, reshaping the equations as the fabric of reality changed beneath them. It was a breathtaking idea. Space-time not as a static grid, but as a dynamic organism, self-correcting, resilient, eternally balancing itself at the edge of infinity. The quest that never ends. Even now, decades later, the ghost of Weinberg's vision haunts every corner of theoretical physics. Each new generation seeks what he sought, a theory that will tame gravity's wild heart, that will bridge the infinite and the infinitesimal, that will let us glimpse the code behind creation itself. Perhaps that theory already exists, buried in the equations of quantum geometry, or whispered in the strange music of string theory. Perhaps it lives in the mind of a young physicist yet to be born. For now, we stand before the mystery, humbled yet hopeful. We stare into the chasm where gravity breaks, and in the silence, we hear something faint but unmistakable. A heartbeat. The heartbeat of the universe, calling us to keep searching. The gravity that refused to break where space itself begins to fade. At the vast scale of galaxies and stars, gravity is steady, loyal, and predictable. Its strength, the gravitational constant we know as 6.7 times 10 to the power of -11 cubic meters per kilogram square second, is the quiet hand that sculpts the heavens. It draws moons into orbit, folds starlight through the lens of space, and holds the entire cosmic web together with invisible grace. But as we dare to shrink the scale, as we dive inward, beyond planets, beyond atoms, down toward the trembling edge of the quantum world, this constant begins to shift. Gravity, the most steadfast of forces, starts to tremble. At first, it grows stronger, as if reaching for a final crescendo. But then, astonishingly, it halts not in infinite fury like the other forces of nature, but at a finite peak, a summit far higher than what we observe in the macroscopic world. And from there, it begins to fall. As the scale of distance collapses toward zero, the gravitational constant itself fades, slipping toward nothingness. It is as though space, weary from the strain of matter's pull, begins to resist less and less. At the smallest imaginable scales, space-time simply stops responding. It no longer bends, no longer curves, no longer fights back, it falls silent. Where infinity yields to stillness, this breathtaking vision lies at the heart of asymptotically safe gravity, the theory that Steven Weinberg once described with bold simplicity, a gravity that does not break. In this model, the gravitational constant depends on the scale growing, peaking, and then vanishing as we approach absolute smallness. This graceful curve, this cosmic choreography, saves physics from its most ancient nightmare. The singularity, where Einstein's equations predicted infinite density at the heart of a black hole, or the very beginning of time, Weinberg's gravity says, no more. In his universe, there are no infinities. No point where matter must be crushed into oblivion. No moment when time must fold into itself and vanish. The gravitational constant bends but does not break. It guards the universe from mathematical collapse. It is as though the cosmos itself possesses an instinct for survival, a built-in safeguard woven into its laws, ensuring that it never destroys its own foundations. A theory that solves its own puzzle. In many ways, asymptotically safe gravity feels like the universe finding an answer that was hidden in plain sight. It is the theory that solves the very question it poses. And perhaps that's not so strange. Physics has never been about passing tests. It has been about finding truths that fit the world. If a theory feels like an answer to itself, perhaps that is a sign it is walking the right path. But there's a cruel twist. While the mathematics sings beautifully, we cannot yet hear it in nature. To test Weinberg's vision, we would need to probe the Planck scale 10 to the power of -35 meters, a distance so small it makes an atomic nucleus look like a galaxy. Our instruments, mighty as they are, stand hopelessly short. The Planck world remains sealed behind a veil of impossibility. We can write the equations. We can dream the theory, but we cannot yet touch it. And so, the question lingers. Is asymptotic safety the universe's true law, or simply another elegant mirage on the horizon of understanding? When space becomes a mosaic, there are other dreamers, two physicists, who look at the Planck scale and see not smoothness, but texture. The loop quantum gravity theorists whisper a different story, that space-time itself is not continuous at all but granular, that beneath the illusion of smoothness lies a sacred geometry, tiny, indivisible cells of space, each edged with the exact length of the Planck scale. In their vision, the universe is a cosmic mosaic, built not from atoms of matter, but atoms of space. No measurement smaller than the Planck length can exist, because there is nothing smaller. Below that threshold, the question dissolves. Asking what lies beyond is like asking what comes before the first note of a song. There is no before, there is only silence. And in that silence, the universe rests. Beyond the edge of knowledge, whether Weinberg's graceful curve or the loop theorist's lattice of space holds the truth, we do not yet know. Both stories point toward the same horizon, the same yearning to reconcile the infinite with the finite, to find order in the trembling chaos of creation. Perhaps the truth lies somewhere in between. A universe that is both continuous and discrete, infinite and bounded, eternal and momentary all at once. For now, our mathematics reaches upward, like hands stretching toward a distant light. We cannot yet touch it, but we can feel its warmth. We can sense that the answers are there, waiting, shimmering, just beyond the limits of our instruments, and perhaps even our imagination. And maybe, when the day comes that we finally peer past the Planck veil, we won't just see equations. We'll see the face of reality itself smiling back. The symphony of strings when the universe sings its hidden song. There is a theory, a whisper that has echoed for half a century through the corridors of modern physics called string theory. To some, it is the holy grail of science. To others, a mirage shimmering on the horizon of knowledge. Yet whatever it is, it dares to rewrite the story of reality itself. In the beginning, physicists imagined the building blocks of nature as points, infinitesimal dots, vibrating in the emptiness of space. But the closer they looked, the more treacherous the mathematics became. At the smallest scales, the numbers turned violent, twisting into infinities that shattered all sense. And so, string theory offered a way out, a vision at once poetic and profound, that every particle in existence, from the photon that lights the dawn to the quark within your bloodstream, is not a point, but a string, a microscopic filament of vibration. The music beneath matter, imagine it, an orchestra so vast that its instruments are woven into the very fabric of space-time. Each string vibrates at its own frequency, and each frequency gives birth to a particle. A photon is one note, an electron another. The symphony of the universe itself. In most versions of the theory, these strings are astonishingly small, no longer than 10 to the power of -35 meters, roughly the Planck length. That's 100 billion times smaller than a proton. At such scales, we can no longer talk about particles colliding. We can only speak of strings dancing, coiling, stretching, intertwining in dimensions we can neither see nor fully imagine. And here lies the miracle. Because strings have size, they smooth away the infinities that plagued quantum gravity. They limit how wildly space-time can twist and how deeply energy can dive. You cannot push them closer than their own length, because they are already the smallest units that exist. Where the loop quantum gravity theorists declare, below the Planck scale, nothing exists, the string theorists reply, below the Planck scale lies music, the hidden vibration of existence itself. The third way to infinity. In this light, string theory offers a third path through the chaos. Loop gravity bans infinities by imposing strict limits on space. Asymptotic safety tames them with mathematical precision. But string theory does something far more graceful. It sings them away. By giving matter a rhythm, it turns destruction into harmony. The impossible infinities of energy that once tore our equations apart are now capped by the finite motion of strings. Virtual particles, once infinite in number and mass, become constrained, each a ripple in the same cosmic chord. Even the internal infinities of Einstein's relativity, the singularities that doomed black holes and the Big Bang to physical absurdity, are softened by the finite nature of strings. No two strings can collapse to a single point. They have size, they have presence, they refuse to vanish. At the heart of creation, there is no singularity. There is only sound, the trembling note of the cosmos giving birth to time. The dilemma of the invisible. And yet, for all its elegance, string theory suffers the same wound as its rivals. Its beauty is mathematical. Its evidence, ethereal. Just as loop gravity depends on the existence of discrete cells of space, string theory depends on the existence of strings themselves, entities so small that no experiment can yet touch them. We search for their echoes in high-energy collisions, in the cosmic microwave background, in the whisper of gravitational waves, but the universe remains silent. The proof, if it exists, lies far beyond our reach. And so, string theory remains both masterpiece and mystery. A cathedral of equations without a cornerstone. The fourth vision, Hamada's quantum horizon. But now, in the year 2025, a new contender steps into this ancient arena. A quiet mind from Japan, Kenji Hamada, has proposed something extraordinary. A theory that blends the clarity of Weinberg's asymptotic safety with the elegance of string theory's infinity-canceling grace. His creation bears the formidable name, renormalized, background, free quantum gravity. Like Weinberg, Hamada does not populate his universe with new objects. No strings, no loops, no lattices of space. Instead, he reshapes Einstein's equations themselves, introducing a mathematical refinement so subtle that it bends infinities into finitude without breaking the form of the theory. But here's the wonder. What began as pure mathematics, abstract, cold, almost alien, seems, upon reflection, to possess physical meaning. The equations whisper truths that mirror the behavior of the universe itself. In Hamada's vision, space-time is not built atop a background, it is the background. It breathes, adapts, and evolves from the quantum chaos beneath it. The divergences that once shattered our understanding dissolve naturally, as if the universe were correcting its own script. The edge of understanding. We stand now before four paths to the same impossible summit. The asymptotically safe gravity of Weinberg, where constants flow like rivers that never flood. The loop quantum gravity, where space is a mosaic of indivisible tiles. The string theory, where reality is music written in the key of 11 dimensions. And now, the Hamada model, where the equations themselves awaken into new life. Each seeks to bridge the unbridgeable, to reconcile the vast with the tiny, the eternal with the ephemeral. Perhaps none are wholly right. Perhaps all are. For the universe is a poet, not a machine, and every great theory is but one stanza in its song. And as we gaze into the depths of the unknown, we can almost hear it, the faint vibration beneath existence, the hum of a billion strings, or perhaps a single, infinite silence, reminding us that every equation, every theory, every human thought is merely another way the cosmos learns to speak its own name. Space-time as an elastic being. To understand Hamada's revelation, think of Einstein's space-time as a serene sea fluid and obedient. Under small disturbances, ripples spread freely. The sea bends as gravity commands. But Hamada's space-time is more like a cosmic ocean with hidden tension in its depths. For small waves, it behaves gently, just as Einstein predicted. Yet as the tides rise and the waves of gravity grow monstrous, something remarkable happens. The ocean stiffens. The resistance grows not linearly, but quadratically, like a spring that becomes harder and harder to stretch. The stronger the pull, the greater the resistance, until at last, space-time itself refuses further deformation. Mathematically, this rebellion appears as additional terms in Einstein's equations, terms proportional to the square of curvature to the square of the Ricci tensor. To most people, these are symbols, but behind them lies a breathtaking truth. Hamada's equations make infinity impossible, the end of the infinite. In a single, elegant sweep, Hamada's mathematics erases both of physics' most haunting infinities: the quantum infinities, born from the violent froth of virtual particles, and the Einsteinian infinities, the singularities that tear space apart in black holes and the Big Bang. In Hamada's universe, no black hole collapses into a point of infinite density. No region of space curves until it breaks. The elasticity of space-time rises to meet the crushing gravity, halting the collapse just before it becomes absolute. Even the wild foam of quantum particles, that restless sea of creation and annihilation, is tamed. The vacuum may still quiver with energy, but space-time itself, after a certain threshold, refuses to stretch any further. The very structure of the cosmos learns when to stop. It is as if the universe, through Hamada's lens, possesses a form of wisdom, a self-correcting intelligence that prevents its own destruction. The spring of creation. And what does this mean for the beginning of everything, for the Big Bang itself? In Hamada's story, the birth of the universe was not an explosion out of nothingness, but a cosmic rebound, a vast spring released after being wound too tightly. Picture this. Before expansion, the cosmos was in a state of extreme compression. Matter had condensed so densely that the gravitational field became immense, stretching space-time like a rubber sheet drawn to its limit. According to classical physics, this should have led to a singularity, a collapse into oblivion. But Hamada's space-time had other plans. Just as a trampoline bends under weight, space-time stored the energy of that compression within its elastic core. At some critical moment, the pull of gravity and the push of elasticity balanced perfectly. Then, by sheer inertia, the compression went a little too far, space-time was overstretched, humming with tension, and then release. The elastic fabric rebounded, flinging outward with a force unimaginable, releasing the pent-up energy in a blaze of expansion. That moment was our Big Bang, not a detonation, but a cosmic spring awakening, the fabric of reality snapping back from its deepest curve. It's an image both intimate and grand, a universe that first inhaled before it exhaled, a cosmos that fell inward, only to leap toward infinity, the poetry of a living universe. What makes Hamada's theory so haunting is its simplicity. Unlike the loop theorists, he introduces no new building blocks of reality. Unlike string theorists, he invents no hidden dimensions. Instead, he refines what already exists, space-time itself, endowing it with the grace of resilience. In this universe, there are no bottomless pits, no tearing infinities. Only rhythm, only balance. Black holes no longer end in nothingness. They pulse, like lungs between contraction and release. The universe itself is a living system of tension and harmony, of compression and freedom, an eternal conversation between gravity and grace. And if Hamada is right, then perhaps the Big Bang was not the first word in the story of time, but merely a breath, one of countless inhalations and exhalations of a living cosmos that never truly began and will never truly end. The cosmic trampoline, Hamada's universe in motion. The universe, in Hamada's eyes, is not a one-way story. It does not simply begin, expand, and fade into silence. It breathes, it oscillates. It lives through cycles of expansion and contraction, like a cosmic heartbeat, like a diver plunging into the depths only to rise again. Picture the cosmic trampoline once more, the boundless sheet of space-time stretching, compressing, and rebounding. Each downward plunge the era of compression stores unimaginable energy in the elastic fabric of existence. Each upward leap, the era of expansion, releases that energy in a breathtaking surge of light and creation. We are now riding one of those upward leaps, our present expansion cycle, the universe still soaring from the rebound of its last collapse. But Hamada did not stop there. His theory does something extraordinary. It dares to explain what set that first upward motion ablaze. The dawn of inflation. In the beginning of our current cosmic breath, something miraculous occurred, a fleeting moment called cosmic inflation. For a heartbeat of time, a fraction of a second, about 10 to the power of -32 seconds, the universe ballooned at unimaginable speed. swelling by a factor of 10 to the power of 50 or more. In that instant, what had once been smaller than an atom expanded beyond the size of galaxies. The very geometry of space-time unfolded like silk under a sudden gust of wind. Scientists have long known this inflation must have happened, for the fingerprints of its violence are etched into the cosmic microwave background, the afterglow of creation itself. Yet no one could explain why. What mechanism had lit that fire? Hamada's vision provides a breathtaking answer. In his analogy, the inflationary epoch was the moment when the trampoline of space-time, stretched and compressed beyond its balance, began to snap back. The universe, overly tense from the compression that preceded it, rebounded with colossal force. The elastic membrane of space-time, desperate to release its stored energy, hurled everything outward at a speed faster than comprehension. Inflation, then, was not an explosion, it was a recoil. The universe was leaping upward, its very fabric releasing the energy of its own deformation. The hidden children of gravity. Yet Hamada's theory holds another secret, a quiet revelation shimmering in the darkness between the stars. Within his equations, there emerged not just the known gravitons massless, invisible carriers of the gravitational field, with spin 2, but also another, heavier kind of excitation, a particle with no charge, no color, no light, only mass. He called it the dark particle. These particles, born from subtle ripples in the gravitational field itself, interact only through gravity. They are ghosts untouchable by light, beyond the grasp of our detectors. They do not shine, they do not scatter, they do not burn, but they exist. And in their silent congregation, they form the unseen scaffolding of the cosmos. Like phantom architects, these dark particles shape the galaxies, bending the motions of stars, sculpting the large-scale structure of the universe. Where ordinary matter is the paint, dark matter is the canvas, vast, invisible, and essential. In Hamada's framework, these heavy, hidden particles arise naturally. They are not an afterthought, not an addition to patch a hole in cosmology. They are the inevitable echo of his gravitational equations, a manifestation of the same elasticity that governs spacetime's rise and fall. At the subatomic level, gravity is too weak to reveal them. But across the grand sweep of the universe, their collective mass whispers through the motion of galaxies, through the slow pull of clusters, through the subtle bending of light from distant stars. They are the invisible heartbeat of the cosmos, the dark choir that sings gravity's deepest song, a universe that never dies. In Hamada's model, nothing is truly born and nothing truly dies. Each collapse becomes the seed of a new expansion. Each expansion carries within it the memory of the last. Black holes no longer mark the end of time, but the beginning of new worlds, where compression breeds rebirth. Inflation, once a mystery, becomes a natural consequence of spacetime's elastic recoil. In dark matter, the universe's greatest enigma, reveals itself as the heavy breath of gravity's hidden rhythm. The universe, then, is not a static sculpture, but a cosmic dancer, swaying between tension and release. A divine heartbeat, a trampoline of eternity. And perhaps, as Hamada suggests, every age of the cosmos, every cycle of expansion and collapse, is not merely repetition, but evolution. With each rebound, spacetime remembers. It refines, it learns, until one day, the universe may awaken fully to its own rhythm and know that even infinity has a pulse, the unreachable horizon where theory waits for proof. And so, we arrive at the quiet truth that lingers at the edge of all discovery. Hamada's renormalized, background-free quantum gravity stands not merely as another attempt to tame the wild heart of spacetime, it stands as a masterpiece of imagination, a theory that unites elegance and restraint, simplicity and depth. It offers what others only hinted at, a refined physical mechanism that dissolves infinities, explains cosmic inflation, reimagines dark matter, and restores harmony to the most chaotic corners of the universe. In the great cathedral of quantum gravity theories, Hamada's vision gleams like stained glass catching the first light of dawn. But even the most brilliant idea must wait for the hand of experiment. For now, the universe remains silent. Our technology, our detectors, our colliders, our telescopes cannot yet touch the Planck frontier where Hamada's equations come alive. We cannot confirm them, nor can we disprove them. His theory, like so many others before it, lives in that shimmering twilight between mathematics and measurable truth. And therein lies the eternal challenge of quantum gravity, the divide between thought and observation. Theorists have built magnificent castles in the realm of pure intellect, crafting frameworks that could reshape everything we know. But the experimentalists stand on the ground below, their instruments still too small to reach the stars of that new reality, the promise of the future. Yet, this is not cause for despair, it is a call to wonder. Every mystery that now defies us is a promise of what humanity will one day uncover. Across the world, scientists work tirelessly to stretch the limits of what we can measure. Quantum sensors more precise than ever before, gravitational wave observatories listening for the faintest tremors of spacetime, particle accelerators that probe closer to the Planck scale. With each passing decade, each one brings us a step nearer to the truth Hamada glimpsed. And when that day comes, when the veil is lifted, and we finally see how gravity moves through the quantum sea, we will not just understand a new law of physics. We will understand ourselves, our hunger to know, our courage to imagine, our refusal to stop reaching. So tonight, as you watch this, remember that every equation is a map, and every unanswered question is a doorway. Somewhere, perhaps in a lab not yet built, or in the mind of a young dreamer watching this very moment, the next great leap of discovery is already beginning. And when that leap comes, we will finally hear what space-time has been trying to tell us all along. Until then, we keep listening, we keep searching, we keep believing.